Hey, before you watch this video, be sure you've seen what this Newton's clicker can do. If you've never seen one of these in real life, check out the Wikipedia page. It shows some animations. The thing about these is that if you lift one ball and drop that ball, exactly one ball will come off the other side. If you drop two balls will pop off the other side when the two balls come down and collide. And the point of this video is to show with physics why it is that when two balls are dropped, two balls must come off instead of just one. I showed this to a class a while ago and then asked them this question on a test and nobody got it. So maybe watch this video multiple times, or definitely send me an email and tell me if you get it or not, or what it is you don't get about it. So to show what would be wrong with one ball coming off when two balls are dropped, we have to figure out what velocity that ball coming off would have if momentum is going to be conserved in the collision. And we know momentum has to be conserved in this collision because there's no external forces acting. Momentum must be conserved between the instant before the collision and the instant after the collision. So when we figure out the momentum of this system before the two balls hit, we have to look at the very instant before they hit, when they've built up as much speed as they're going to build up. So let's call that speed right before the two balls collide 1 meter per second. And then theoretically, after the collision, they would come to a complete stop, and theoretically, in this hypothetical situation, one ball would fly off the other side. And so, using the conservation of momentum, we have to figure out what velocity it would have. And we're just going to say, to keep things simple, let's say each of these balls weighs 1 kilogram. And this velocity we're solving for is the velocity of this ball the instant after it flies off. We know gravity is going to slow it down really quick, but we're not interested in what its speed is 50% of the way up. Just that one instant when it's going as fast as it's going to go right after the collision. And what you might do is look at this intuitively and see that these two balls on the left are coming to a complete stop, so they're losing all of their momentum. And if momentum is conserved, all of that momentum that they had must be transferred to the one ball on the right. There we go, back to one ball on the right. So you could write up a little equation based on the conservation of momentum. Momentum initially before the collision equals the final momentum after the collision of this whole system of balls, that is. And we could see that the momentum before is held in these two balls on the left. So we could say the mass of the two balls times the velocity of the two balls equals the final momentum. And we could see that after the collision, the only thing that's moving, and hence the only thing that has momentum, is the one ball on the right. And let's say R for the one ball on the right. R for right. The velocity of the ball on the right after the collision. Let's change these subscripts of 2. I don't like them. A subscript of 2 often means a final, but that's not what it means here. So let's use L to mean the two balls on the left. So that's one valid way we could set up this equation. But let's be more technically thorough about it. In our math here, let's reflect the fact that we know that the momentum that is conserved is of the system that encompasses both the balls on the left and the balls on the right. So to be very thorough about this, we'd have to include both mv for the balls on the left initial and the momentum of the ball that's going nowhere on the right initially, because we know that the MV for the ball on the right before anything hits it is 0, but technically this is the way we should set up the equation. We would have to do this if we had a problem where two things were colliding that were both moving before the impact. So this term is the PI, the momentum of the system before the impact, and let's get an expression for our PF, the momentum of the whole system after the impact. So that would include the final momentum of the two balls on the left and the final momentum of the two balls on the right. Oops. That's an F there. So really, this big whole equation here is what we should use to solve for the velocity of the ball on the right. So this is our variable that we're solving for. But we can simplify this a lot because we know that the velocity of the ball on the right starts at 0 before the impact. So this whole expression is 0 and we can just get rid of it. And we know that the two balls on the left come to a stop after the impact. So the final velocity of the balls on the left is 0, and that makes this term 0, and we can get rid of that. So what we're really left with is MV for the balls on the left equals the MV of the balls on the right. And that's exactly what this is. So the point of all this is just to show the more technically accurate and thorough way to get our simplified equation. So back to getting down to business here. To figure out what the speed of the one ball coming off the right must be if momentum is conserved, and we know momentum is conserved, we just have to solve this equation. So actually let's plug in the numbers first. We know that each ball is 1 kilogram, so those two balls on the left must be 2 kilograms, and we've said that their velocity right before impact is 1 meter per second, and the one ball that comes off the right only has a mass of 1, and there's the variable we're solving for. We can see that that velocity must be 2. So I'll put that down here. And remember, this is all a theoretical situation, because we know that it's not actually one ball that comes off, actually two balls comes off. And here's why. We have to consider the kinetic energy of that one ball that comes off compared to the kinetic energy of the two balls that come down. Right before impact, those two balls are coming up to high speed, and the speed they have at that high speed they have right before the impact, that's the most kinetic energy they're going to have. We know kinetic energy is half mv squared. These two balls have a mass of 2 kilograms, and their velocity we said is 1. So the kinetic energy of those two balls right before impact is half times 2 times 1. Oh, that's 1. And that was for the two balls. Now let's look at what kinetic energy would that one ball have if there were only one ball that came up, and it came up at 2 meters per second. And we know it would have to be 2 meters per second because that's the speed it would have to conserve momentum. So let's find the kinetic energy that it would have. Again, kinetic energy, half times the mass of that one ball times the velocity of that one ball, which is, so we know that's 2. 2 squared is 4, times a half is 2. So here's the problem. We would go from 1 joule of kinetic energy to 2 joules an instant later, as soon as the one ball on the right comes away from the others. And we can't just be pulling energy out of thin air. energy can always interconvert between different forms, but this joule of energy, this extra joule that we have going from here to here, that didn't come from potential energy or elastic energy or electric energy or anything like that. It just kind of came out of the blue. So this cannot happen. This is impossible. So we have shown that because kinetic energy would have to be gained in this collision if only one ball came out, there would in fact have to be two balls that pop out in order for both momentum and kinetic energy to be conserved. Because if one ball came out, there would be like a 200% elasticity. And we've seen that even 100% is impossible.